So for this video, we'll be continuing our discussion on mechanical waves. So far we have learned about the types of mechanical waves. We have transverse, we have longitudinal waves. We also have surface waves. And we also learned about the mathematical description of a wave. So if we have the wave function, we will know what are the properties of the waves. Now, so we have the speed of a transverse wave. One key property of a wave is its wave speed. So take note that the wave speed is related to the frequency and the wavelength. We just have to multiply the frequency and the wavelength and we will get the wave speed. And the wave speed of a wave in a particular medium is constant. So for transverse waves on a string, we can actually obtain the speed of the wave in terms of the tension of the string and the mass per unit length. So we have this equation. We have V is equal to the square root of uh, F sub t over mu, where F sub t is the tension on the spring and mu is the linear mass density. So the linear mass density is just equivalent to the mass per unit length. So we have m divided by L of the string. So the tension on the string is given in newtons, while the linear mass density mu is given in kilograms per meter. Okay, so we can see from this equation that if we increase the value of the tension of the string, then there will be an increase in speed of the wave. So the speed of the wave increases if the tension of the string will increase. So there is a direct relationship between the two. While the mass per unit length and the speed is inversely related, meaning to say, if we increase the value of the mass per unit length, then our V decreases. So we can further write this as this is equal to the square root of F sub t divided by mu, which can be expressed as mass per unit length. So we have this equation, F sub t multiplied by L over m. So we have the square root of the tension multiplied by the length divided by the mass. So let's try to answer this quick quiz. We have here the 6 strings of a guitar are the same length and under nearly the same tension, but they have different thicknesses. On which string do waves travel the fastest? So we have this equation in order to know. Okay, so we have V is equal to the square root of F sub t times L divided by M. Now for the 6 strings of the guitar, they are nearly of the same tension and of the same length, but the thickness varies. So there are strings that are thin and there are also strings that are thick. The thickness of the string is directly related to its mass. The thicker the string, the more massive it is. So, as you can see from this equation, if we increase the mass of the string, then that means our speed would decrease, or small values of m will have greater values of v, and large values of m will get small values of v. That means to say that the waves travel the fastest on the thinnest string. Okay, this should be the correct answer. Now, the previous equation for V is for a transverse wave in a vibrating string. Remarkably, it turns out that for many types of mechanical waves, the expression for wave speed has the same general form. So we have this one, we can generalize it as V is equal to the square root of the restoring force returning the system to equilibrium divided by the inertia resisting the return to equilibrium. So in the case of the wave on a string, the tension on the string is the restoring force that tries to return the system into equilibrium. And mu, which is the mass per unit length, is the inertia resisting the return to equilibrium. Now let's talk about the energy in wave motion. So every wave motion has energy associated with it. As an example of energy considerations in wave motion, let's consider again the transverse wave on a string. From the property of mechanical wave, energy is transported along the length of the vibrating string, and this instantaneous rate at which energy is transferred is referred to as power, and its value is dependent on both position x and time t. In mechanics, we have defined power as the rate of energy per unit time, or this is equal to work per unit time. And work can be expressed as force uh, multiplied by the displacement, and then we have this one, or we can have F times V, since displacement over time is just equal to this, the velocity. So if we have this wave function representing the wave on a string, we have y of xt is equal to a, say for example cosine kx minus omega t. You can actually get the velocity v of xt, which is just equal to the partial derivative of the wave function with respect to time. So we have minus a sine kx minus omega t multiplied by omega, or this is now a positive value. And we can also get the slope. So we have obtained the slope that is equal to slope. You can write slope, which is equal to the derivative of the wave function with respect to x. So we have a negative sine. So we have sine kx minus omega t, and the derivative of this one, we have positive k. So we have minus a k sine kx minus omega t. Now for a string that is moving from left to right as described in our wave function, so we can have any point on the string in which at this point we call it point A. The string to the left of point A is exerting a force to the string to the right of point A. And this force is represented by this one. So this is the x component of the force. And we also have the y component of the force. So we can call this f sub y And then this one, we can call it f. Now take note that if we divide f of y by f, this is just equivalent to the negative slope of the string, which is just equal to the negative of the partial derivative of y with respect to x. So we have the change in y divided by the change in x. So from this equation, we can have f sub y is equal to negative f multiplied by the slope. Now let us go back to our expression for power. So power is equal to f times v. Now this f here is equivalent to f sub y. Therefore, we can write power as negative f partial derivative of y with respect to x multiplied by the partial derivative of y with respect to time, which is just equivalent to the transverse velocity of the spring. Okay, so that we can write power dependent on the position and the time is equal to negative f times the partial derivative of y with respect to x is we have negative ak sine kx minus omega t, kx minus omega t multiplied by the velocity, which is equal to a omega sine, we have kx minus omega t. So from the previous expression for p, we can write p of xt is equal to f times a squared omega k sine squared kx minus omega t. And if we use this relationship, then we can get this expression for power. So we have power p of xt is equal to the square root of mu times f. We have omega squared a squared. We have sine squared kx minus omega t. And we can have our P max, the maximum power of the wave, is equal to mu times f omega squared a squared. So we can get P max when the value of our sine squared theta is equal to 1. And the average power of the wave is just equal to 1/2 multiplied by mu times f omega squared a squared, or this is just equal to 1/2 of the maximum power. Now it is important to note that the power of a wave, or the energy that is transported through wave motion, is directly proportional to the square of the amplitude as well as the square of the frequency. Now, waves on a string carry energy in just one dimension of space, that is along the direction of the string. But other types of waves, including sound waves in air and seismic waves during earthquakes, carry energy across all three dimensions of space. For waves that travel in three dimensions, so we define intensity as the time average rate at which energy is transported by the wave per unit area. Or mathematically, we can just write intensity denoted by I is equal to the average power per unit area. And the unit for intensity is watt per meter squared. Now, if waves spread out equally in all directions from a source, the intensity at a distance r from the source is inversely proportional to the square of r. If the power output of the source is P, then the average intensity I through a sphere with radius r and surface area 4 pi r squared is this one. We have I equals P divided by the surface area of a sphere, which is 4 pi r squared. So for example, if we have the source of wave propagation here, then if this is r1, r sub 1, and this one is r sub 2, then we can say that the power at point 1, this is at point 2, is just equal to the power at point 2. That means I1 multiplied by the surface area 4 pi r sub 1 squared is just equal to I sub 2 times 4 pi r sub 2 squared. So we can cancel 4 pi and we are left with this one, I sub 1 r sub 1 squared equals I sub 2 times r sub 2 squared. Or we can have this ratio. We have I sub 1 over I sub 2 is equal to r sub 2 squared over r sub 1 squared. So we call this relationship the inverse square law for intensity, which means that the intensity I at any distance r is therefore inversely proportional to r squared. Now you might want to try this quick quiz before we proceed to our next topic. Okay, now let us look at the behavior of waves when they meet a boundary or when they meet another wave. So far, we have been discussing waves that propagate continuously in the same direction. But when a wave strikes the boundaries of its medium, all or part of the wave is reflected. So for example, when you yell at a building wall or a cliff face some distance away, the sound wave is reflected from the rigid surface and you hear an echo. So the echo is actually a representation of the reflected sound wave. Now, if two or more waves meet, they can also interfere. So let us see how are waves reflected and how are they when they overlap. Now let us look again at transverse waves in a stretched string. So what happens when a wave pulls or a sinusoidal wave arrives at the end of the string? So as you can see, we have here two strings that are attached to a support. So as soon as the wave, or we call this the incident wave, arrives at the boundary, the waves travel back to where it started. So we have here two types of boundaries. We have a free end. So imagine you have a pole here, and then our string is attached to a pole such that it can move up and down. And then we have here another string that is attached to a boundary that is a rigid support. So it is fixed at the boundary. Now, notice the difference of the two reflected waves. So for the free end, the displacement of the string is the same as that of the incident wave. So for example, the incident wave is along the positive y direction, then the reflected wave is also in the positive y direction, while for a fixed end, the reflected wave is reversed. So the incident wave is moving in the positive y direction, or the displacement of the medium is in the positive y direction, and for the reflected wave, the string is displaced in the opposite direction. Now this is because of Newton's third law of motion. So as the spring, or as the wave reaches the boundary, it exerts a force toward the support. And in return, the support exerts a force that has the same magnitude but in opposite direction as the force exerted by the wave. So that is why the reflected wave is reversed. Now, for example, if we have two strings that are tied together such that the first string has a different mass per unit length as that of the other, then the point where they are connected can serve as a boundary. So for example, if we have a thin string and a thick string that is tied together, then this will be the behavior of the wave. So there will be reflection and transmission. So part of the wave will be transmitted and some parts of the wave will be reflected. So take notice of the behavior of the transmitted and the reflected wave. So this is from thin rope to a thick rope. So take note that the thin rope has lesser mass per unit length compared to that of the thick rope. So as you can see, when the incident wave reaches the boundary, some of the wave will be transmitted and the direction of the transmitted wave is the same as that of the incident. But take note of the direction of the reflected wave. The reflected wave is inverted. Now another example is from a thick string to a thin string. So this is from a string that has greater mass per unit length compared to the thin one. So from thick to thin. So take note that the amplitude of the wave increases as the wave is transmitted into the thinner string, while the direction of the reflected wave is not reversed, but take note of the amplitude. The amplitude of the reflected wave is lesser compared to that of the incident wave. When two or more waves overlap in the same region of space, the resulting effect is interference. The resulting amplitude The resulting amplitude can be either larger or smaller than the amplitude of each individual wave, depending on whether the waves are in phase or out of phase. So, when the waves are in phase, the result is called constructive interference. When they are one half angle out of phase, it is called destructive interference. So when two waves overlap, the displacement at any point is the algebraic sum of the displacement of the corresponding points of the overlapping waves. In other words, the wave function y of xt that describes the resulting motion in this situation is obtained by adding the two wave functions for the two separate waves. This is how we illustrate constructive interference. So we have two wave pulses that are traveling in the opposite direction. So one is moving to the right and one is moving to the left. Now during the overlapping, the amplitudes of the wave will add up. And after they overlap, the two waves will move in the same direction as they were moving. If this is your wave 1, this is your wave 2, then wave 2 will move in the same direction as it was before. So there is no reflection. And wave 1 will move in the same direction as it was before, as if nothing happened to them. Okay, so unlike particles, they cannot overlap because particles cannot be at the same point at the same time. But waves can be at the same point at the same time. Now for destructive interference, now we have two waves um, moving. One is moving to the right and then the other is moving to the left. Take note that the first wave is along the positive y, or is displaced along the positive y, and then wave number 2 is displaced on the negative y. Okay, now as soon as they overlap, their amplitudes will also add up. But since the other one has a positive displacement and then this one has a negative displacement, then it appears their amplitude cancels out. And then after they overlap, again, there will be no reflection. They will move as if nothing had happened. So wave number 1 will move, wave 1 will move to the right, and then wave number 2 will move to the left as if nothing happened. Now, if the two waves have the same amplitude, then during the overlapping, we have a total constructive interference in this case, and we have a total destructive interference for this case. Constructive interference occurs when the path difference r sub 2 minus r sub 1 is equal to the integral multiple of the wavelength. So we have r sub 2 minus r sub 1 is equal to n times lambda, where n is equal to 0 plus minus 1 plus minus 2 plus minus 3 and so on. While destructive interference occurs when the path difference r sub 2 minus r sub 1 equals that of the half integral number of the wavelength. That is, we have r sub 2 minus r sub 1 is equal to n plus 1 half multiplied by the wavelength, where again n is equal to 0 plus minus 1 plus minus 1 plus minus 2 plus minus 3 and so on. So this is for constructive interference, and then this one is for destructive interference. Now, during the interference or during the overlapping, what happened is this. We have the principle of superposition. So the principle of superposition of waves states that y of xt is equal to y sub 1 plus y sub 2, or the wave function, the overlapped wave, is equal to the algebraic sum of the displacements of the individual waves. Thank you so much for watching, and please comment, like, and subscribe to our YouTube channel.